Hello, welcome to Electronics Education. This is Vincent Chang. I have prepared, this is the 8th lecture I've prepared. You are supposed to learn 7 lecture around the feedback. So this lecture is gonna tell you that how much you have really digested from the previous 7 lectures. Because our goal is to train you, to teach you how to solve a practical feedback amplifier. So this lecture is going to be a test to test you if you really understand everything what you learned from the previous 7 lectures. It's the case, an example of the non-inverting operational amplifier. Here's a non-inverting operational amplifier. The blue one is the operational amplifier. The RID is the input differential resistance. The lowercase RO is the output resistance of the op-amp. And the mu represent the voltage gain of the op-amp. Right? We have included the RS and the external load, also the feedback network. So the question here, I said this is a test, but I'm not going to grade you. So, but I strongly encourage you to pass. Maybe I think you need about 10 minutes to find out the input resistance are in and the output resistance are out. And closed loop voltage gain VO over VS. The voltage gain with feedback. You need 3, I think you need about 10 minutes. Remember, let me just give you a hint. Remember 3 steps? The step 1, sketch the A circuit. Step 2, calculate beta. Step 3, plug in the ideal formula. I think the most challenging part is going to be the step 1. So I'll be back in about 10 minutes. I'm back. Have you solved this? Can you solve this? First of all, this is the feedback network. The purple one is the feedback. I think you can easily recognize this is the feedback. But what topology? What topology? Look at the left-hand side is the series mixing. It's obviously the series mixing. And then it's the shunt sampling. So it's the series shunt. Obviously, it's the series shunt feedback. Input resistance? But no, not input resistance. For the left-hand side is the series. I'll have explained this. I was trying to use the question mark to ask you what type of mixing, but I already told you. Series mixing, and look at the note, it's the shunt sampling. So voltage mixing and voltage sampling. Series shunt feedback. So let me repeat the circuit diagram on the left-hand side. And this is the real case, the real series shunt feedback on the right-hand side. So remember the 3 steps. Step 1, the A circuit. Draw an A circuit by yourself. Calculate beta and plug in. Sketch the A circuit. To assist you to easily digest the lecture you learned from this, then I did this on purpose. I just bring back the one I show you in the previous lecture. Here. And then let me duplicate this as a reference when we sketch the A circuit. Don't touch the basic amplifier, right? just duplicate the basic amplifier. So just duplicate the basic amplifier. RID, mu, and the lowercase RO. Then what? Call in the RS. Come on. Come on in. And then come on in. Call in RL. Come on in. Then what? Then it's kind of weird. You have to do something. It seems out of nothing. No, it's out of something. It's out of the feedback network. You have to consider the loading effect of the feedback network. So you have to add the parallel combination of R1 and R2 and series combination. Am I going too fast? Let's go back. Let me ask you, let's stop for a moment, okay? Why parallel combination of R1 and R2? Why? Are you with me? Are you with me? I said you have to what? The RA. This is the RA. The identity of this resistance. The parallel combination of the two resistance is RA. So what's the definition of RA? It comes from the H11. So here's the definition. You have to short circuit the output of the feedback network and looking from the left, from the input side. Short circuit the output and looking from the left, from the input side, from the port 1. Right? So focus on the green node. Okay? Focus on the green node. So when you short circuit the output of the feedback, the right hand of the R2 is grounded. So grounded is connected to grounded between what's the resistance between the green node and the ground? The parallel combination of R1 and R2, right? You get it? That's RA. So now, why I put on the series combination of R1 and R2? Why? That's RB. The RB is defined by 1 over H22. The trick is to have to set I1 0. You have to set I1 as 0. You have to open circuit the input side. So when you open, this is R2, this is R1. When you break, you open circuit, you cut. Okay? You open circuit the input side and looking from the green node. See the green node? Looking from the green node. So what's the resistance between the green node and the ground? When you open circuit the top line of the R1, you see the series combination of R2 and R1. Right? That's it. That's RB. So this is your job, to draw an A circuit, an open loop gain circuit. Get it? We're still on the step 1. Then what? Then you can calculate, for example, the capital RI, the series combination of the three. The RA is defined by the parallel combination of R1 and R2. Same thing with the RO, capital RO. The capital RO, the output resistance without feedback. The parallel combination of the three, O, B, and L. And the voltage gain, the open loop voltage gain, VO divided by VI, is quite easy, okay? I leave this to you. Step number 2, calculate beta. So what is beta? Beta is defined by a parameter called H12. But the trick is you have to set I1 as 0. You have to set I1 as 0. So when you set I1 0 and the V1 divided by V2, let me copy. When you cut the top line of R1, this is R2, this is R1, cut the top, you set I1 0. That means what? These two resistors share the same current, okay? Share the same current divider. Voltage divider, V1 divided by V2 divider. So it's the divider. All right, voltage divider. R1 divided by R1 plus R2. So once you get beta, then the final step, you can just plug in. So you can just plug in, then ideal formula. Here's the outcome. Wait. No question for the closed loop voltage gain, but there's a difference between RF and Rin. I was asking you the red Rin. I was asking you the red R out, excluding the load resistance. I was asking the red Rin, excluding the source resistance. Okay, so this is a tiny nitty-gritty detail. So for the RIF, it's the resistance looking from the source. So you have to deduct RS, take out the RS, then becomes the RIN. RIN series with RS equals RF. So here's RIN. For the R out, the parallel combination between the R out and the RL equals ROF. So ROF now is given, RL is also given, then you can go back and track the output resistance, the R out. Here's the answer. You can check the math by yourself. I'm not going to prove this in detail. So how to solve a practical feedback amplifier? How to solve, once you identify, it's the series shunt topology, 3-step. Number 1, sketch the A circuit. But the trick is, sometimes the most challenging part is to find out the RA and the RB, the hometown, the loading effect. Step number 2, calculate beta. The final step, plug in the ideal formula. I hope you enjoy the lesson, you learn from the feedback and become more confident because you already understand not just the idea, also the key concept for a practical amplifier and the skill that you need to solve a practical amplifier. This is the end of the lecture video. Thanks for watching.